Guys, we're going to try this. Let's see. All right. Characteristics of acids. Okay, they react with acid, or sorry, react with metals. pH less than 7. Let's see, H ions. So you're going to have more of those than the OH minus ions. Sour. Used in foods. 2, 3, 4, 5. Oh, I'm missing one. What is one? I could never remember what that last one is. Oh, turns blue litmus red. It turns blue litmus paper red. All right, bases. Slippery. pH greater than 7. Hydroxide ions. Taste bitter. Used in cleaning products and cleaning products. Turns red litmus paper blue. All right. Okay. Arrhenius. Arrhenius said an acid was a proton donator. Arrhenius, remember older name, sounds Greek, actually 1903. Hydroxide donator. So he basically said the only way they differentiate is in their base definition. Bronsted-Lowry also said that an acid is an H donator, but he said that a base is a H proton acceptor. So he kind of changed the definition based on NH3. Or they changed the definition. So, proton donator, OH donator, OH, or proton acceptor. That is the big difference. Remember that these have conjugates, and these produce water plus a salt. I'm going to put a salt because it can be any salt. So that's how you'll be able to tell an Arrhenius acid-base reaction versus a Bronsted-Lowry. All right, identify whether the following substances are acids or bases. I'm just going to go through all this, even though on your own. It's just how it's going to be. Taste sour, that's going to be an acid. Changes red litmus paper to blue, that's going to be a base. Turns phenolphthalein pink when it gets to be basic. So basically, you're putting it into an acid in a beaker, and it is clear. And then you are adding base till the base takes over. And then once it's a basic pH, then it turns pink. Changes blue litmus paper red, that's acids. Reacts with metals, that's acids. Feels slippery, that's bases. Tastes bitter, that's bases. Feels like water, that's acids. pH greater than 7, that's bases. Feels like water, okay, same one twice. They like it so much that they have to put it on there twice. Identify the following as acid, base, or neutral. Vinegar, that is an acid, that is acetic acid. Alkaline, that is a term for a base. Lemon juice, that is edible, it is an acid. pH 3, below 7 is an acid. Bleach is a cleaning product, so that's a base. pH of 7 is neutral. Ammonia is NH3, that is a base. Coffee is an acid. NaOH is a strong base. I see the hydroxide right there. Pure water is neutral. Ooh, sorry. Okay. Given the formula, choose the correct answer. An Arrhenius base and acid. Okay, so I see I'm not making water and a salt here. So this has nothing to do with Arrhenius. This has to do with Bronsted-Lowry. And so this is the guy that's giving up the hydrogen. I find him on the other side without his hydrogen. So this is my acid. This is my conjugate base. This is water, which is amphoteric acting as a base. This is my conjugate acid, hydronium. And so HClO4 is an example of a Bronsted-Lowry acid because a proton is donated. That is D. I mean, the only other thing you could say HClO is an example of an Arrhenius acid but it would have to say a proton is donated, and it says it is accepted, and that is not what is happening. Classify each of the following compounds as an Arrhenius acid or an Arrhenius base. All right, Arrhenius bases are easy. They have hydroxides attached to them. So base, and again, hydroxide base, hydrogen out front acid, hydrogen out front acid. And that's page 1 in the books. Hopefully this autofocus will do whatever it's going to do. How come my hand is so in focus? Do I need to lower this? If I lower it, does it? Not really. I mean, it kind of focuses better, but I don't know. All right. Well, anyway, that's page 1. Page 2. What is a conjugate acid base pair? Well, I'm not sure what they're asking here. I can give you an acid conjugate base pair. I can give you a base conjugate acid pair. Or I can give you both the conjugates, the conjugate acid and the conjugate base. So when you ask me a very general question about what is a conjugate acid base pair, I'm going to suppose that they're wanting you to answer this. What are the conjugates on the other side? And those are the species after a hydrogen has been donated. And accepted. So yeah, the species after the hydrogen has been donated and accepted are the conjugate base and acid pair. Otherwise, you're going to have to ask that question in a better way, like this one, number 2. I can absolutely answer, not a problem. What is the conjugate acid of H2O? Well, since this is acting as a base, bases turn into conjugate acids. There is my conjugate acid. It is H3O plus 1. Make sure that your charges are done right. Why is it plus 1? Because it accepted a proton. Got one more positive charge than negative charges. That's also something to think about with acids. This is amphoteric acid. It has one more hydrogen it can give away, which in this case it is acting as the acid. It can also accept one. So it can become H2SO4 sulfuric acid. So anything that's got a hydrogen out front, just make sure you're taking care of the charges of what's actually happening. The conjugate base of HBr. So this is my acid. Acids turn into conjugate bases. My conjugate base is Br minus 1. That is the Br by itself with an extra electron. Okay. Identify acid base, conjugate base. So if this is the acid, then I'm going to see ClO4 minus on the other side. Oh, there he is. So this thing is acting as an acid, which means water is acting as a base. That means bases turn into conjugate acids Acids turn into conjugate bases. Follow the bouncing arrow. All right, now we have a bunch of things that are amphoteric. We have water, we have sulfuric acid, we have all kinds of things that are amphoteric. But if this is acting as the acid, then I should see HSO3 minus on the other side. There it is. If this was acting as the acid, I would see OH minus on the other side, not to be found. So I know this is the acid, this is the base. Bases turn into conjugate acids. Acids turn into conjugate bases. Okay, what are the conjugate bases for the following acids? Well, if I get rid of a proton, then I have ClO4 minus. Minus. Make sure that minus is visible there. Minus. You're getting rid of a proton, which means you keep the extra electron. So that's what happens. Here, OH minus. Again, I'm keeping the extra electron, but I'm sending away the proton, so OH minus. What are the conjugate acids for the following bases? Here I have a negative charge. If I make this hydrocyanic acid, then I have no charge. And that is definition of a conjugate acid is something that has accepted a proton. There it is. And it is H3O plus. Remember, adding a proton makes that plus charge. There, H3O. Hopefully this camera will live long. Can you stay in focus for 1 freaking second? All right, what is the conjugate acid of CO3 minus? It's going to be HCO3 minus because it's going to gain a hydrogen. Oh, they put it right there. Don't even have to, you just have to find it. What is the conjugate base of NH4? Well, if that's acting as an acid, then NH3 is my conjugate base. Acid, conjugate base, base, conjugate acid. Although these are Bronsted, that's a, let's not talk about it. Identify the acid base, conjugate base. If this is the acid, I'm going to see PO4 3 minus over here. 3 minus. I don't see that. So he clearly is acting as the base. Water is acting as the acid since he's giving away the hydrogen. Acids turn into conjugate bases. Bases turn into conjugate acids. H2CO3, HCO3. He's the guy that gave away the hydrogen. He's the guy that accepted it. Conjugate acid, conjugate base. Remember, acids turn into conjugate base. Bases turn into conjugate acids. Bases turn into conjugate acids. Acids turn into conjugate bases. What are the conjugate bases for the following acids? NH3. After he gives away a hydrogen, he's no longer positively charged. CO3 minus 2, because now he's given away another proton. What are the conjugate acids? Oh, conjugate bases? Yeah. What are the conjugate acids for the following bases? HSO4 minus, he gained a hydrogen. H2CO3, he gained a second hydrogen. That's what happens to bases that turn into conjugate acids. Bases accept a hydrogen, conjugate acids have that hydrogen. All right, so that is page 2 in the book. What are we at, 14 minutes in? Yeah, let's just keep going. What does the term amphoteric mean? Can act as an acid or a base. I mean, water is an amphoteric. HSO4 minus, because it can give away a hydrogen. It can also accept a hydrogen and become H2SO4. If you see a hydrogen out front, chances are it could act like amphoteric in one way or another. How can one determine if an acid or base is strong? Well, you could plug a light into the solution and see how light it brights up. You could check percentage dissociation. Strong acids dissociate 100%. You could check pH. If it's a pH between 0 and 2, that's a strong acid. What is pH and what does it measure? It is the power of hydrogen. Potentia of hydrogen, power of hydrogen. We can make believe that that's what it is. Nobody really knows. We know that it says potens and a hydrogen, but there's also a Q by an H later in that same book. So power of hydrogen, what does it measure? The concentration. Let's just put concentration. Concentration of hydronium ions. Notice it doesn't measure the hydroxides because that's a POH that does that. What pH values determine whether a substance is acidic, neutral, or basic? So pH less than 7 is acidic. pH greater than 7 is basic. pH of 7 is neutral at 25 degrees. What is POH and how does it relate to pH? Well, pH plus POH equals 14. That's on your formula sheet, so no problem there. Easy to figure out. Acids with are strong acids, while bases with a high pH, low pH. So again, 0 to 2 for strong acids and 12 to 14 or a pH for a strong base. But remember, a POH is just like a pH. The lower you go, the stronger your base. So do not get POH and pH confused. Hopefully you won't. Which of the following pHs would be the strongest acid? Whatever the lowest pH is the strongest acid. Full stop. Whatever the highest pH is the strongest base. pH 1, pH 13, prototypical strong acid, prototypical strong base. Solution A has a pH of 4, while solution B has a pH of 6. Which solution is more acidic? That would be A. Lower pH, the more acidic. What is the pH of a solution with a POH of 9.5? 14 minus 9.5 equals what? 5.5? 5.5. Right? 14 minus 9.5. Let's just make sure. 4.5. What am I doing? My math. Jeez. Oh, come on, Erwin. POH. Oh, sorry, pH. We were calculating pH from a POH. POH 9.5, 14 minus 9.5. 14 minus pH equals POH. 14 minus POH equals pH. Okay. Sodium hydroxide has a pH of 14 and baking soda has a pH of 9. So sodium hydroxide is stronger than baking soda. Coffee has a pH of 4. Stomach has a pH of 1. Coffee is weaker acid than stomach acid. Solution A has a pH of 2, while solution B has a pH of 5. Solution 2 is more acidic. Solution A, sorry. A. What is the pH of a solution with a POH of 7.6? 14 minus 7.6 is 6.4. pH equals 6.4. 14 minus 7.6 equals pH 6.4. Okay, page 4. These are all so easy. We've been zooming right through this review, but I'm going to slow down when we get a little further on. What is a neutralization reaction? What kind of reaction is it? It is an acid-base reaction, acid-base, and more specifically, Arrhenius. Arrhenius did this because he gives us like an HCl plus an NaOH. We'll know it because we'll see the hydroxide, and I see the hydrogen here. And if I add those things together, I get salt. In this case, literally salt plus water. Whenever you see water and salt, that is an acid-base, an Arrhenius neutralization reaction. Neutralization reaction. How does water form from the acid and base in a neutralization? Well, you have the H plus combines with the OH minus to make a H2O. That's what a neutralization reaction really is. It's H pluses plus OH minus. What is the titration? When is it used? When you need to determine the concentration of an acid or base. Generically is when it's used. A titration is when you add a certain amount of acid or base until you get to an equivalence so that you have an equal number of moles of acid and base. They will be equal to each other. Once they are equal to each other, then we can put them in MAVA. MA times VA equals MB times VB, and it will give us the molarity of our acid. So basically, we know how much base we used, we know the molarity of the base we used, we know the volume of the acid we started with. We can calculate the molarity of our acid using that. What are some acid-base indicators? Red litmus paper, blue litmus paper, phenolphthalein, which you'll never phthalein. Yeah, those are the indicators that we've used. Hydrion paper, there's a whole bunch of other indicators. And you use them during titrations. So during titrations to indicate equivalence. That's their main job. They indicate equivalence. They tell us where to stop. So we need to know where to stop our titration so that we have equal moles of acid and base. General equation for a neutralization reaction is up there. What would you use to clean a strong acid spill? You want a strong base. Because basically you're trying to neutralize the acid. Now, what they usually do is they water it down because that decreases the molarity, right? If you put strong acid, but then I add thousands of gallons of water to it, that's why you wash your eyeballs out. If you get acid in them, you wash them in the wash because you're basically neutralizing the acid by making it much less concentrated. How could you determine if a substance was an acid or a base? I could use pH. I could use litmus paper. If I plunge a blue piece of litmus paper into something and it turns red, I know it's an acid. If I plunge a blue piece of litmus paper into that same substance, or a red piece of litmus paper into that same substance, it wouldn't change color at all. What equation is used to solve titration problems? The molarity of the acid times the volume of the acid. Remember, this doesn't have to be liters. You just have to use milliliters on both sides. The volume of the base times the molarity of the base. So we're going to calculate some titrations here. I've been given 43.55 milliliters of a 0.30 molar base. This is going to be my base. How do I know? Because it says hydroxide there. And it just took that much to neutralize 20 milliliters of my acid. So what I need to know is what is the molarity of my acid. So 43.55 times 0.3, enter, divided by 20 milliliters, I get a 0.65 molar acid HNO3 solution. What is the molarity of 100 milliliters of an unknown base can be titrated? So again, now they've given me 85 milliliters of acid, and they've given me the molarity of it, and it's 100 milliliters of base that we have titrated. So we need X molar base. 85 times 2 enter divided by 100 enter is 1.7 molar. 1.7 molar base. What is the concentration of 45 milliliter sample of HCl if it requires 28.3 milliliters of a 2.5 molar base to neutralize it? X molarity. So again, we're just plugging numbers in and calculating. 2.5, as long as you get the numbers that go together, divided by 45, 1.57. I get 1.57 molar HCl. They gave us what the acid is, might as well use it. All right, that's the first 4 pages. I think I'm going to stop this video, and then I'm going to continue on in the next video.